Now let us see how to calculate the sensitivity and specificity for a given model. Now let us take this fiber bits data. On this fiber bits data we are going to build a logistic regression model. So here is the logistic regression model. Now let us see how to calculate the sensitivity and specificity of this model. We have already seen how to validate this model and what are these names of the each variable and their description in logistic regression. Now let's see how to calculate specificity and sensitivity. To calculate sensitivity and specificity, we need a matrix, confusion matrix. So we use the library caret. So we need to install caret for calculating sensitivity and specificity. So let's keep the threshold as 0.5. So the logistic regression output is probability. So in our fiber bits model 1, when we predict, the output will be probability. So when the probability is more than 0.5, we are saying 1. When the probability is less than 0.5, less than or equal to 0.5, we are classifying it as 0. So that's why threshold is 0.5. That's what exactly threshold 0.5 means. So we are finding out the predicted values using fiber bits model 1. So here is the threshold value, which is 0.5, and predicted values with the threshold of 0.5. Predicted values are 0 and 1. There are 40,000 zeros with 59,000 ones. Okay, and these are the actual values for this model, and confusion matrix is actual versus predicted. Let us print the confusion matrix. So this is the confusion matrix. Accuracy is nothing but diagonal elements upon overall sum of all the values. Now what is the sensitivity? True positives upon overall positives. So how many times we have actually predicted 0 as 0 over and above all the zeros. So the sensitivity for this particular model is 73%, specificity for this particular model is 78%. So sensitivity is 73%, specificity is 78%. Now when we change the threshold value, if we say for this particular model, when we get the predicted probability, if the probability is more than or equal to 0.8 or more than 0.8 then 1, otherwise 0, then definitely number of ones and number of zeros will change, because we have now changed the definition of 1 and 0 classes in the predicted model. So let us see, if we change the threshold to 0.8, what is the new updated sensitivity. So this is the confusion matrix for the new model, and the sensitivity for the new model is 55%. The specificity, actually specificity increased, sensitivity reduced. So we have made more errors in this case compared to previous one. Similarly, when we change the threshold to 0.3, we can see that sensitivity and specificity values change. This time the sensitivity is increased to 92%. When we say threshold value is 0.3, whichever is more than 0.3, whichever probability is more than 0.3, we are classifying it as 1. Whichever probability is less than 0.3, we are classifying it as 0. In that case, obviously the number of zeros and ones change. Zeros are lesser, ones are more. Out of all the ones, how many of them we have correctly classified, how many of them we have wrongly classified. So 92% is the sensitivity and 68% is the updated specificity. So based on the threshold value, based on what is 1, what is 0, what is the class that we are defining in the predicted probability, based on predicted probabilities, our values of sensitivity and specificity are changing. So this is how we calculate sensitivity and specificity values. We still have one question left: how do we choose the threshold value? Which one is important, sensitivity or specificity? Now we have seen that when we change the threshold value, the sensitivity and specificity are changing, because by changing the threshold value, the good and bad customers classification is changing, the classes are changing, so the sensitivity and specificity will be obviously changed, because number of good predicted good, number of predicted bad have direct sensitivity is depending on number of predicted good and number of predicted bad. Okay, which one of these two should we maximize? Is it sensitivity or specificity? What should be the threshold so that we can maximize either sensitivity or specificity? Ideally we want to maximize sensitivity as well as specificity, because we want to have 0% error, 100% accuracy, so that means sensitivity is really high, specificity is also really high. But it is not always possible, there is always a trade-off. But there are certain class of problems where we want to be 100% sure on predicted negatives, and sometimes we want to be 100% sure on predicted positives. So let us see few examples of where are those classes where we want sensitivity to be really high, where are those classes where we want specificity to be really high and we can compromise on sensitivity. So there are certain class of problems depending on the business problem that we are handling. Sometimes we might have to give very high preference to sensitivity, sometimes we might have to give very high preference to specificity, and we can even ignore sensitivity. So let us see when sensitivity really matters, when specificity really matters. Here is an example where sensitivity is a really high priority and specificity doesn't really matter, or we can compromise on specificity. Now imagine that we are building a model to predict the bad customers or default customers before issuing a loan. So we want to issue a loan based on customer details. We are building a model that will predict who are bad customers, who are going to be default customers. Okay, so the actual classes are 0, yes they are defaulters, 1, no they are non-defaulters. Then the predicted classes are yes defaulters, no non-defaulters. So when actually a customer is really a defaulter, we want to definitely find him as a defaulter. Those are true positives. So actual customer is bad and the model is also predicting them as bad. Now that's a good scenario and we want to maximize it. Now there are few errors that we might make in this particular situation where the customer is actually defaulter and we built the model and our model is predicting him as non-defaulter. So those are false negatives. So we are predicting using the model that he is a non-defaulter, but actually his traits are very similar to a defaulter. So he is a defaulter, but our model is predicting him as non-defaulter. What is the problem there? The actual customer is bad, but we are predicting him as good, so that is an error. Now there is one more error that we might make. Actually the customer is good, he is a non-defaulter, but our model is predicting him as bad, that is as a defaulter, that is false positives. And there is one more accurate prediction that we can do, another type, that is actually the customer is non-defaulter, our model is also saying the customer is going to be non-defaulter. Now out of all these 4 values in this matrix, one of these is really dangerous, that is the second element in the first row, that is false negatives is really dangerous compared to every other type of accuracy or error, because the actual customer is bad, the model is predicting him as good. Then what happens? So when the actual customer is bad and the model is predicting him as good, then this is what happens. So when the actual customer is good, model is predicting him as good. Whenever model predicts the customer as good, then we are going to reject a loan. When the customer is good, we are going to offer a loan. When the customer is bad, we are not going to offer a loan. So when the customer is a defaulter and we are also predicting him as a defaulter, then obviously when the model is predicting him as a defaulter, then we reject a loan of whatever is the loan amount. But the actual customer is defaulter and we are predicting him as non-defaulter,
erroneously, our model is predicting him as non-defaulter, then we will go ahead, because we have predicted him as good, we'll go ahead and issue the loan. Now that is really dangerous, because we are giving a loan to a bad customer and he might not pay back again. Now what is the problem with this, and when we compare this error with another type of error, which is the actual customer is good but model predicted bad and we did not give him a loan. To be honest with you guys, here there is no real risk here. So when the customer is good, we did not give him loan, that means we might be losing on a small delta of profit. But when the actual customer is bad, when we give him a loan, okay, then he might run away with the loan, he might not pay back, he might turn out to be default. Then within this matrix, this false negatives are really highly important. So here we want to really reduce false negatives. That means we want to really increase true positives overall percentage. So out of all the bad, we want to find out each and every bad. So that is what in the sensitivity, if the sensitivity is nothing but true positives by overall positives, and we want to really increase sensitivity, in this case we can compromise on specificity. It's okay not to give a loan to good customers. I mean, it's not really as bad as the earlier case of giving a loan to bad customers. So the profit of a good customer really not equal to the loss by a bad customer. In fact, the loss by a bad customer might be equal to profit of 100 good customers, because this is loan business. At a time we will disburse a lot of loan amount. Okay, in this case bad customer is not equal to a good customer. Okay, if in this case we give the same weightage as false negatives to true positives or false positives, we would be doing something wrong. So we set the threshold in such a way that sensitivity is really high. We don't want to compromise on the sensitivity in this particular situation. Okay, we can compromise on the specificity. It's okay not to give a loan, or it's okay wrongly classify a good customer as bad customer and not to give a loan. We might lose out on the small percentage of profit, that is fine, but it is definitely not okay to give a loan to a bad customer. So this is the case where identifying bad is really critical. That is when we give higher preference to sensitivity. So overall accuracy in itself might not be sufficient. Sometimes we need to give higher preference to true positives percentage, that is sensitivity. Sometimes we might have to give higher preference to specificity. We will see that example later. But in this case, in this particular case, where a bad customer is equivalent to 10 or 100 good customers, then we have to give higher preference to sensitivity. True positives really matter here.